Hey there, Class 10 students. Welcome to this A1 Institute Explainer. Today, we are going to get you completely exam ready by mastering the magnetic effects of electric current. Let's get right into it.
Have you ever really stopped to think about it? How does a fan start spinning? Or how does a speaker actually make sound? It's not magic, it's pure physics. So, how on earth does electricity create motion?
Well, the big secret behind all of this is what happens when you bring an electric current and a magnetic field together. It's like a secret handshake between two of the most fundamental forces in the universe. And this right here is the golden rule. If you have a wire with current flowing through it, and you place that wire inside a magnetic field, the field actually pushes on the wire. This force is the key that unlocks motion from electricity. Okay, so we know there's a force. But which way does it push? Up? Down? Left or right? For your exams, you got to know the exact direction. And luckily for us, there's a kind of cheat code for this. It's called Fleming's left-hand rule. Seriously, this rule is going to be your best friend for solving these kinds of problems. It's a super simple, physical way to remember how the magnetic field, the current, and the force all relate to each other. Let's see exactly how it works.
All right, this is the fun part. I want you to actually do this with me right now. Get your left hand ready. Now, stretch out your thumb, your forefinger, and your middle finger, so they're all at right angles to each other, just like you see on the screen. Each one of these fingers is going to represent something important. So, let's lock this in. Your thumb points in the direction of the force, or the motion. Your forefinger points in the direction of the magnetic field, and your middle finger, that points in the direction of the current. A really easy way to remember this is FBI, force, field, which uses the symbol B in physics, and current, symbol I. Say it with me, force, field, current. You master this, you've mastered the problem.
Okay, the theory is cool, but practice is what's going to make you confident for that exam. So let's put this rule to work right now with a typical exam question. All right, check this out. This is a classic. An electron is moving into the page. At the same time, it's passing through a magnetic field that's pointing from left to right. Now here's the trick, the thing you have to remember. The direction of conventional current is always opposite to the way the electrons are moving. So if the electron's going in, the current is pointing out of the page. Okay, let's use the rule. Get your left hand up, point your forefinger, the field, to the right. Good. Now point your middle finger, the current, out of the page so it's pointing right at you. Now just look, where's your thumb pointing? Downwards, that's it. The force on the electron is downwards. Simple as that. So where do we see this force in the real world? Well, the perfect example, and a huge topic for your exams, is the electric motor. It's the amazing device that makes everything from fans to toys move, all using this one single principle. So here's a basic look at a motor. You've got a rectangular coil of wire, we'll call the sides A, B, and C, D, and it's just sitting there between the north and south poles of a magnet. Then, you connect a battery to send a current through the coil. Now let's focus on one side, arm AB, and use our rule. The magnetic field, our forefinger, goes from north to south, so left to right. The current, our middle finger, is flowing into the page. So where's your thumb pointing? Downwards. Arm AB gets pushed down. Okay, now let's look at the other side, arm CD. The field is still going left to right. But this time, the current is flowing out of the page, back towards us. Use the rule again. Where's your thumb pointing now? Upwards. Arm CD gets pushed up. So think about it for a second. One side of the coil is getting pushed down, and the other side is getting pushed up. What's going to happen? The whole thing starts to spin. It rotates. And that continuous rotation is the magic behind every single electric motor. But the real genius here, the part that keeps it spinning instead of just flipping back and forth, is this clever little device called a split ring commutator. Its only job is to flip the direction of the current every half turn. This makes sure that pushes and pulls keep the coil spinning in the same direction, over and over again. Okay, let's bring this all home. Literally, we're going to see how these exact principles apply to the circuits inside your house, which is another really important topic for your exams. This diagram might look a little complicated, but the journey is pretty simple. Electricity comes in from the main supply, it goes through your electric meter, then it hits a distribution box, your fuse box, and from there, it branches out to all the switches and sockets in your home. Now listen up, because for your exam, you absolutely have to know these 3 wires. The live wire, usually in a red color, is the one that brings in the high voltage. The neutral wire, which is black, is what completes the circuit. And the earth wire, which is green, is the crucial safety feature that protects you from electric shock.
Whew, we've covered a lot of ground, so before we wrap this up, let's do a super quick recap to lock in the most important points you need for your exam.
Okay, so what are the must-knows? Number 1, a current in a magnetic field gets pushed by a force. Number 2, Fleming's left-hand rule is how you figure out the direction of that force. Number 3, this whole idea is the reason electric motors spin. And finally, remember those 3 wires in your house? Live, neutral, and the super important earth wire for safety.
Hey, if this explainer helped clear things up for you, please do us a huge favor at A1 Institute and hit that like button, share it with your friends, and definitely subscribe so you don't miss our next exam-ready session.
And if you want to really boost your preparation with the best notes and expert guidance, please get in touch with us at A1 Institute. All our contact details, including the phone number, are right there for you in the description below. And I'll leave you with this one last thought to chew on. We've spent this whole time learning how electricity can create motion, but could you do it the other way around? Could you use motion inside a magnetic field to create electricity? Think about it, because that's the principle of an electric generator, and that's a story for our next explainer. See you then!